The topic of this discussion is instrumentation and experimentation in information technology research. We will explore the importance of instrumentation and experimentation in advancing the IT field. To be specific, in aiding postgraduate students in doing their MSc or PhD research. Information technology research plays a crucial role in the development of cutting-edge technologies, processing data and information into something that can be applied by humanity. This can be in the form of economic incentives. It can be for the sake of engineering or scientific advancements. IT has a role in all this, and the list is not exhaustive. So in this discussion, we will delve into the significance of instrumentation and experimentation, which drives innovation in research. Before we begin, I think it is beneficial to know the computing space covered by information technology in relation to other related fields such as information system and computer science. According to Association of Computing Machinery, IT covers more on the application, deployment, and configuration aspect of the technology, of computing technology. As in contrast to theory, principles, or innovation. It covers organizational issues and information systems, application technologies, software methods and technologies, and the infrastructure, including cloud. It does not cover on the hardware and the architecture of the computer. Information science is broader and covering more on organizational issues and the use of information systems to address those issues. To address those, information system also studies the application technologies and to certain degree software methods and technologies to solve those issues. Even though it is biased towards application, but there are elements of theory, principles, and innovation, especially from the human side. Computer science is more technical, more fundamental. As you can see, computer science covers largely on theory, principles, and innovation. It is also covering a lot in development, and some aspects of computer science touch application. It is not covering organizational issues. It is also not covering computer hardware. In general, computer hardware and architecture is covered by computer engineering discipline. So in today's discussion, we will relate ourselves to information technology. The research process. This is the generic steps in doing a research. First, we need to identify the problem. The problem can be identified through experience, especially by reading existing works done by other researchers. This is known as literature review. The literature must be from reliable sources, such as journals and some conference proceedings. Having identified the problem from reliable sources, we set the research questions. What do we want to know? What are the problems? How to solve the problems, the specific problems? What are the goals, i.e. the objectives? And what is the idea of solving the problem? The idea of solving the problem comes in the form of hypothesis. A hypothesis is just an idea. Until it is tested, it remains a hypothesis. It remains an idea. To prove the idea works, we have to choose a suitable case. This comes under study design. In study design, we need to identify the data, the algorithm, the infrastructure that are needed to perform the testing. Yeah, it may involve collecting data. The data can be collected before the experiment or before the testing. These are called preliminary data. It's more of exploring the problem and whether we should go further with researching it. If preliminary data shows that there is a merit, there is an advantage of proceeding with the study, then we will come out with the experimentation to collect the actual data. Yeah, it may be an experiment, it may be simulation, it may come in other form of studies. Yeah, once the data is collected, we need to analyze, because some are dirty data, some are not relevant, some are wrong. We try to relate the data to our objectives and problem statement. The goal is always to see whether the hypothesis can be rejected or not. So the hypothesis that cannot be rejected. Usually, actually, we from the hypothesis, we acquire the null hypothesis. We will reject the null hypothesis. If we can reject the null hypothesis, then we can say that the hypothesis is acceptable. Yeah. And finally, we need to present our findings in writing the report. So there may be more than one report. Yeah, the final report, of course, is in the form of thesis. But before arriving at that level, you will be producing a lot of reports on your progress of the work. The report may also come in the form of papers that you submit to conferences and paper and reports you publish as journals. Yeah, and the report will also mention outstanding problems that you will undertake in the future or somebody else will undertake in the future. So research is a cycle. Yeah, it's a continuous cycle. So you are just at this stage of time, you are receiving a baton, like in a relay run, in athletics, in relay run, 4 times 100. You're just receiving the baton from other researcher. You make a round and then you pass the baton to somebody else. Let's begin by looking at research instruments. Instrument refers to the tools, equipments, and techniques utilized to gather data and measure variables in a study. The choice of instrumentation depends on the nature of the research question and the specific field of study, which means that your instrument may be different from the instrument used by your peer, because the problem that you are solving and they are solving are different. Which is why in today's lecture, the number of slides is quite huge, because I'm trying to cover some of the major instruments and research methods. But a method that works for somebody else may not really work for you. So you have to decide. First, you have to know these are the instruments, and then you decide whether you can use the instrument to your advantage or not. So research can be quantitative or qualitative or combination of both. Yeah. If combination is called mix. Now in qualitative, we are looking at qualitative data. Yeah, like classification. It's a qualitative data. So qualitative data is collected in qualitative research. So it depends on your research question, whether it is to identify, to understand certain quality. Yep. Most research begin with qualitative research, and then later on they use quantitative data to confirm the qualitative research. So qualitative research is done by collecting data at a glance in real time from participants who are experiencing the problem. The data can be collected in more than one form. Maybe talking directly through interview. It can be formal, informal interview. Or it can be just being there and observe scientifically and with analytical thinking, not just observing for entertainment, but observing the patterns. The key idea is to observe what is important and what patterns are hidden in the data. And another reliable source of data is existing documents. Okay. So these data are collected. They are analyzed, and you make inferences to identify the pattern in the data, whether it has any significant interpretation or not. So the data that you collect this way from the field, yeah, and they are very raw, and you have to process the data to remove the extremes, to remove the bad data, so that only the data that is genuinely representing the problem is used in the analysis. Yeah, you have to make sure the data is correct and sufficient. Some of the instruments, this is not an exhaustive list. Some of the instruments used in qualitative research, one-on-one interview, or if you have a lot of interviewees, then you can have a focus group. This is commonly used to get response, for example, in studying market's response towards a product, treatment of patients with mental issues. We want to know whether the therapy works or not. You can have focus groups. We can do ethnographic research. This is mainly related to the impact of technology on different culture in different geopolitics. Yeah, especially if you're doing studies more on human-centric, more human-centric studies, like the impact of design on user experience. You may need to do ethnographic research, but it may not be relevant to those people who are doing algorithm studies, to improve performance. Yeah. And then case study research, where you have many examples of such cases. You can dig the reports. You keep the record, because the record that you do from your study will become secondary sources for your research later on. And observing the environment, observing field environment, observing simulated environment. A part of that, we can do narrative research. Narrative research is involving interview and analysis of documents. It's about what other people say. It's about narration. It's about what other people say with regard to a particular topic. So the difference of narrative research as compared to one-on-one interview is that narrative research is done in a long term. You'll be following that person over weeks to months to years. You want to see the progress, what the person says about particular topic over the time. This will give you some insight on and on the impact of the research. The other one is grounded research. In grounded theory research, you look for the explanation. You dig deep to find out why. Why does this thing happen? You're not just studying you're not just doing a descriptive or explorative study. Descriptive study is like, what happened, but you're looking for why it happened that way. So for this, for grounded theory research, you need a lot of data. You need a lot of data to understand how things work. You are looking for gaps. You're looking for deviations. Yeah. And you have to collect the data over the time to see the changes. Now, the other side of the other spectrum of research is quantitative research. Quantitative research is looking at quantitative data. Quantitative data are basically numbers. It can provide you a more focused result because numbers don't lie. Numbers don't lie. Yeah. So qualitative data may have some bias, but quantitative data is more objective. So in quantitative research, again, we may use the same instruments such as survey and questionnaires. The difference is that the question that you ask will help you to collect quantitative data. Surveys and questionnaires are also used in qualitative research, but the question you ask are helping to gather qualitative, like colors, grades. These are qualitative. Yeah. Quantitative may be like height, throughput, speed, basically numbers. Experiments, of course, experiments can, even though experiments can also be used to gather qualitative data, but traditionally it's used for quantitative because we use tools to measure. And then in IT, another good source of data, quantitative data, comes from data logging. Yeah, data logging. Because many of the infrastructure, cloud infrastructures, many of the applications, network analytical tools, they automatically log the data in time series. So this log data is actually recoverable from the folders, and you can use them for your analysis. So from the data, you will do sampling because you don't actually use all the data. You use subset of the data. So that's what we call sampling. Yeah. And then like in a convolutional neural network, you will split the data into training data and test data, right? From the same set of data, you split into two samples, one for training, one for testing. So that is called sampling. And the sampling must be done randomly because if you don't do it randomly, you're just looking for specific quality, then the result is already biased because it's affected by your decision. Yeah, so it must be random. Then from the analytical tools that you use, yeah, statistical tools that you use, you may be able to see categories. You may be able to see the patterns from the correlation. We will get into this, yeah, because to perform reasoning, we need to identify the type of data, whether it's a nominal, ordinal, yeah. Um, are we looking for categorization? Are we looking for relation? Yeah. So it involves advanced statistical analysis, data representation, and then interpretation of the data. In IT, the use of tools and techniques is to measure two aspects: the function of the technology. What does it do for the client, for the user? Yeah. What does it do? IT functions. The other aspect is IT qualities. So ask yourself, your PhD topic, is it addressing an IT function, or is it addressing qualities? If you are addressing optimizations, yeah, improving the speed, improving the security, that is IT qualities. But if you are studying whether certain framework is improving user experience, uh, um, in let's say maybe can help a child with learning difficulty to learn better. That is IT function. That not quality, but IT function. So if you look back at ACM computing curricula, yeah, the IT functions very much relatable to application. Yeah? Whereas IT qualities are more on the development side of it. There are different instrumentations in the field of IT. This is not exhaustive list. In network research, yeah, there are many tools. I'm not mentioning the specific tools here, yeah, because you can explore them on your own. You can just Google them. You can use ChatGPT to find out the tools that are very much suitable to your work, yeah, open source tools or proprietary tools. These tools are used to monitor the network traffic because we cannot see with our naked eyes, so we need tools to see the packets at certain nodes in the network, right? We want to find the bottlenecks. We want to see the traffic patterns. We want to see if there's any abnormality. Yeah, that's from network. Then we also have tools for performance evaluation of an application, of a system. Yeah. This can be in the form of throughput, the volume, the jittery rate, yeah, um, um, downtime, yeah, and then log analysis, as I mentioned, a lot of software applications and software systems actually in the background they generate logs, data files that shows the performance, or if there's any abnormalities, it will generate logs for the faults that happen. Code profiling, if you are developing algorithm in Microsoft Visual Studio, in Eclipse, in any of the IDE, they are actually utilities to profile the code. You can actually measure whether the algorithm is using a lot of memory, RAM memory. It's taking out a lot of storage space, virtual memory. Is it taking a lot of processing power? These code profiling tools will be very useful when you want to study the performance of an algorithm. So I'm not going specific into specific brand. Yeah, you can find them all over in different tools depending on the type of research you do. And then on the extreme end is user experience evaluation. Okay, this tool can be in the form of computerized tool. Yeah, like for example, eye tracking, to to see where the eye is looking at and for how long on specific software interface design. Yeah. Two, paper and pen tools. It does not necessarily have to be software tools. Yeah. So we have talked about qualitative research, quantitative research. Then in reality, there are many research where both types of data are involved, in which we need to apply mixed method. Yeah, because both types of data are collected for that particular research. Now, you ask yourself, your research is more on the quantitative side, qualitative side, or both? If both, is it more qualitative or more quantitative? So there are differences for both. I think both side has its use. Maybe you start by doing qualitative to narrow down, then only you do quantitative. Qualitative to narrow down, then you use quantitative to confirm your hypothesis. Okay. Qualitative research is good when you are not clear about the solution. You want to produce the hypothesis. So once you produce the hypothesis, right, the next thing that you want to do is to test the hypothesis. To test the hypothesis, you have to set up experiment, simulation, suitable research method. This kind of setting will produce quantitative data that you will use in your analysis to confirm or to reject your hypothesis. I hope so far it is clear that both quantitative and qualitative are used. Quantitative is usually more on confirming the hypothesis. Qualitative is usually in the beginning of the research to help you understand, to help you explore and understand, and to build a good hypothesis. Let me share with you one example, not from IT, but more from commercial point of view. Yeah. Now, this is about television. Samsung, as you know, is a popular brand for handphone, but prior to making handphone, they actually produce a lot of electronic and electrical gadgets. They even venture into construction and shipping. Yeah, it's not just a smartphone. So in 2000, Samsung wants to redesign its televisions. So at first, it does qualitative study. It uses ethnographic reports to see what consumers say about Samsung television and other brands of television. So from the qualitative, so they may be giving questionnaires, maybe they give out prizes for those people who answer the questionnaires. I mean, they can use any kind of tactics to gather the data. And depending on what they ask in the questionnaire or interview, yeah, you determine whether it's ethnographic or not. Ethnographic actually has some demographic elements like the background of the target respondents, yeah, like maybe gender, age, job, geographies, ethnicity, things like that. The finding is that most people do not watch TV during the day because they're working. And they view TV as a piece of furniture more than electronics. So Samsung starts thinking, okay, what can we do using this finding? Of course, for Samsung, their job, their business is to make television, a part of other electronics, to make television and to sell television to make profit. So that's their objective, right? So based on that objective, what can they do with this finding? So with this finding, they have an idea. Since people don't watch TV that much and they view it as furniture, they view it as furniture. That means the furniture must look nice, right? People want something that looks nice in the living room. So the TV must be designed like furniture to look nice in the living space. So that's the idea. But how do they know that this idea will work or not? They do. So they form the hypothesis, then they want to test the hypothesis, right? So they do quantitative research. So they design a new TV, produce the new TV, okay, with speakers hidden below the TV. They make it very, very thin so that it can be put on the wall, yeah, and look very modern. Um, when I when the customer is not using it, it can show beautiful screen that makes it look like a picture frame, but actually it's a TV. All right. So after they produce that, they have some sample customers, or maybe real customers purchasing it, and they collect feedback from them. This time they may use questionnaire also, but the questions that they put in the questionnaire generate numbers. Maybe they use Likert scale. Yeah, I mean they use Likert scale. They use tools like CSAT to get quantitative data, so they can produce statistics and get an evidence to support that this new TV design is actually better than before. So this is an example where both quantitative and qualitative methods are used, aka mixed method approach. So how to choose depends on your problem statement, your research question, and your objectives. Yeah, because from there, you will come up with the methodology. So the methodology you may come up on your own, or you may refer to existing literature review. Yeah, because usually people will share what kind of data they collect, the method they use to collect the data, and then how they analyze the data. So you get information from those literature, okay, and and you see whether your work is in nature similar to those work or not. Then you can probably employ the same methodology and methods. So those papers also mention how they collect, how they analyze, how they check. So they check for validity and reliability, maybe using statistical approach. Yeah, and also be mindful when you're collecting data. You must know the ethics. Yeah, the confidentiality and privacy of participants. Yeah, and to redistribute the data. You must get the consent. I mean, all these things. I don't need to elaborate because this something that um by common sense we should know. Yeah, and another aspect that you must be careful when choosing the research instrument is how much time you have, and whether you need to fork out a huge budget to collect this data. Do you need to come up with a prototype and then use the prototype to collect data, or it's something that you simply just produce questionnaire and distribute to some students to collect the data? That one is cheap. If you have to produce a prototype, some more is involving making a hardware prototype before you can actually do the experiment, then it require much longer time and budget. So you must take this into consideration, because when you do research, you have time limitation. So there are many methods to do research. And in today's discussion, I want to look at experimentation as one of those methods. Yeah, there are other methods. Experimentation is employed in IT research because it can provide a controlled studies. Yeah, it can help you to narrow down the factors that affect your study in a controlled environment. Okay. Now, how do we come up with a good experimentation? And why do we want to do experimentation? Experimentation is a method to collect a data to validate our hypothesis. Sometimes an experiment shows that the idea doesn't work. So whatever we learn from the experiment is used to improve the idea, to refine the idea, to refine the hypothesis. Now, let's look at this. Richard Feynman, an American theoretical physicist. So theoretical physicist or theoretical researcher, and in this case, Richard Feynman is somebody who studies physics, like maybe quantum computing, this kind of thing, or maybe people in the field of astronomy. A lot of them are doing theoretical studies. They use mathematics to analyze, to infer a new idea, and to prove the idea. All done on paper using mathematics. Yeah. Now that's one way of doing it. The other way is to carry out experiments. Yeah. To carry out experiments to find out whether the idea works or not. Now, according to Richard Feynman, it doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment, it is wrong. So what does that show? You may have a very good idea, but the experiment doesn't agree with it. That means your idea is wrong. Empirical studies is very important to confirm an idea. No matter how nice it is, in mathematics, in statistics, looks nice, but experiment doesn't show, so it is wrong. So what is experimentation? Experimentation is one of the methods used in research process. Okay, the difference is that it uses a very scientific method. It's very methodical. That means if the step is not correct, the outcome may be biased. We shouldn't trust it. Yeah, it needs evidence. It needs evidence to come up with a conclusion. So it is the same thing as the conventional research process. You make an observation. Okay, whether and like for us, when we start with the research, we do literature review, right? We read other people's work. But it can also by observing the nature, by observing in the lab. Okay, and then ask the question: why this thing's happening? Why this weird thing's happening? Or why is this pattern occurring? I use my idea, I use my knowledge and understanding, I use my discussion with my professors, with other people, my peer, and come up with a possible explanation. Maybe because of this. This is called hypothesis. Hypothesis is just idea. Maybe it happened because this way. Maybe if we do like this, it will work. That's called hypothesis. But we do not know whether it will work until we test it, right? Until we do the experiment. So we have to figure out the method to collect the data to prove or disprove the hypothesis. And then the data is analyzed. And finally, you conclude whether the hypothesis can be accepted or rejected. And then you report the findings in the form of papers or journals, or a report to an organization. Experimentation in IT share a lot of similarity with other fields. Yeah, after all, it's scientific, but it does have some differences. So what are the differences? Number one, we are playing with IT hardware, IT software. We want to understand the behavior and performance of these IT elements. Because of that, they may be specialized software tools and techniques. These tools and techniques can be framework, can be development environment, can be a simulation software, networking equipment, or measurement analytical tools that we use to design, implement, and analyze the experiments in the research. IT research, because we use software tools or maybe some hardware tools, they produce a lot of data. So we have to plug the correct data, remove the bad data. We can use data mining approach, machine learning approach, statistical analysis, or visualization, to uncover the patterns, the trends, and eventually insights after you look at the trend. So what do you gather from there? Researcher must carefully design experiments to account dependencies between different components and possible cascading effect to ensure meaningful results. Now, if you do programming or you design software architecture, you will realize that one component you modify, the modification effect is not just on that component, but it will affect many, many other components, sometimes jumping to components a few connections away. So this is what we call cascading effect. So in IT research, we have this problem. So we modify this, it will affect many, many other things. So if we modify somewhere else, it may modify our component that we want to study. So we must be aware of that. Okay. Not like maybe in a biological experiment. So the modification is done in the petri dish. So whatever happens only in the petri dish, right? It won't jump out to the neighboring petri dish, or from the neighboring petri dish, it won't jump into this petri dish. So not for software. And then when we do experimentation for IT, often we found out that we're not just doing inside the lab. Actually, most of the experiment may need to be carried out in real world settings or simulated environment that is as close as possible to the real world setting. Because we also need to know whether this thing can be used or not. Remember, IT is also about application, right? It's not just about theoretical aspect. So how does experimentation help your master, help your PhD? Well, experiment is very convincing. It gives you data. It gives you data to support your claim. Yeah? And then experiment gives you very, very specific result. It's not broad. It's very specific. If you design an experiment to show that user attention can be improved when you keep repeating the same element again and again, then the result is either showing that or no. So it's very, very specific. And then even though it's specific, you can apply the findings to other areas which are similar to it. So experimentation has this advantage. And you can have cause and effect analysis of the hypothesis based on the data that you have collected. So you can do projection. Yeah, you can do projection. And any experimental work will lead to more experimental work in the future. So experimental research is about hypothesis testing. What are the steps? Okay, number one, come up with a hypothesis. Hypothesis requires you to come up with a conceptual framework. If you're doing PhD, you may want to start from theoretical framework. From theoretical framework, which is very, very abstract, maybe in the form of mathematics, in the form of ideas. You come up with a conceptual framework from the theoretical framework. Conceptual framework, the difference with theoretical framework is that conceptual framework is an example of theory in practice. Concept is theory in practice. Now, when in practice, you have variables such as time, such as height, such as speed, such as weight, such as amount, such as volume. So conceptual framework will give you variables. Theoretical framework may not give you the variables. So you cannot come up with a hypothesis unless you have a conceptual framework. If you start with theoretical framework from other people's literature review, then you have to come up with a conceptual framework. If you already have the conceptual framework from other people's literature review, then you can straight away come up with a hypothesis. It depends where you start in your research. All right. So once you have the hypothesis, no, it's good to have only two variables, but it's possible to have more than two variables. Yeah. Usually it's good to have two because we want to see the impact one variable on another impact on another variable. So example, one variable is year. The other variable is height. So let's say you want to study how tall children can grow to at certain age. So you need two variables, right? Not age, which is a independent variable because we set the variable, and then height, which depends on the year, right? That is dependent variable. So at least there are two variables there already. So the hypothesis is what? Maybe the hypothesis is that as year goes by, as years increase, the height of children increase. So it's a positive correlation, right? Year increase, height increase. So is this idea, is this hypothesis true or not? Let's test it. Now, to test an idea, you cannot test directly using the hypothesis. You cannot do like that. You must come up with the opposite of the hypothesis. You must come up with a null hypothesis. So if our hypothesis is that as year increases, the height of children increase, then the null hypothesis is the opposite of that, right? As years increase, the height of children will drop. The null hypothesis, then we need to derive the null hypothesis from the hypothesis. Then in our experiment, we try to prove the null hypothesis. If the experiment fails to prove the null hypothesis, then our hypothesis is acceptable. Okay, our hypothesis is acceptable. But if the null hypothesis can be proven, that means our hypothesis is wrong. Yeah. Now, in experiment, you don't do it only one time. At least you do it 2 times. Because if you do it one time, it may be just lucky. It just may be a matter of luck. But if you do it 2 times, then it's not luck anymore, right? And if you can do it more than one time in different setting and still yielding the same conclusion, that is better. So what is hypothesis? If you ask yourself, do you think you can answer this on your own? What is hypothesis? It's an idea, right? An idea, a testable idea, a testable prediction. So hypothesis is usually a cause and effect relationship involving 2 or more variables. Yeah, it's a cause and effect relationship. It can be before, after. Before, after. Or you increase the independent variable, what will happen to the dependent variable? This is cause and effect, right? Cause and effect can be through time, before and after, or one variable affecting another variable. What type of data? The data must be quantifiable, quantitative data, because we want to see the changes, right? So we need to identify the variables, for example, years and height of children. And then what to observe? You observe if these variables change, how it impacts the subject qualitatively. What is changing is quantity, right, from the experiment. But when you do the analysis and discussion, we want to know how the change in quantity impact the quality. Do you see that? How the quantity impact the quality. All right? Because numbers itself is meaningless until you interpret. So what is interpret? Interpret from the numbers. From numbers, you identify the pattern. Pattern is quality. Classification is quality. Right or not? So from quantity, you identify the quality. So how do we do it? We can do it inside the lab. But for IT, it's not just lab. Yeah. Maybe for the chemist, definitely it has to be inside the lab. But for IT, we can also do it in the field. Yeah. Maybe in classroom, maybe in certain organizations. But you try to minimize the factors lah. If you do in the field, you have to make some assumptions, because in the field, the challenge of doing a field study is that there may be a lot of factors that we cannot control. But if we do it inside the lab, then we can have a controlled environment. We can minimize the factors and study only the factors that we are interested in. But we have to do field study sometimes because in IT especially, we do the research because we want to apply it. We do the research before because we want to apply it, and therefore we have to do field study because only field study can give the most realistic environment. Lab environment, yes, good, but it's controlled, right? So maybe you can do it in a controlled environment. Then later on, you repeat again the experiment in the field to validate the findings from the lab. Okay. So you do literature review to come up with a theoretical framework or conceptual framework. Some literature review already give you the conceptual framework, and if you believe that the conceptual framework is true, then you can start from the conceptual framework. But if you don't believe the conceptual framework, then probably you look at the theoretical framework and derive conceptual framework from the theoretical framework. From the conceptual framework, because conceptual framework is theoretical framework in practice. Theoretical framework in practice is conceptual framework. Yeah. From the conceptual framework only, you can identify the independent variables and dependent variables. From the independent variables and dependent variables, you make a prediction. You put your idea forth. You put forth your idea. So the prediction your idea is called hypothesis. From that hypothesis, you determine what data you need. What data you need to collect in order to prove or disprove the hypothesis. But of course, I mentioned just now, from the hypothesis, you come up with a null hypothesis. And then you collect all the data related to the hypothesis and use the data. You try to use the data to reject the null hypothesis in order to prove the hypothesis. Okay? Maybe tongue twisting, play of words, but basically that's what you do. Okay? So the data that you have collected, right, you have to organize it in different task groups because you want to establish the cause and effect. Yeah. So you run the experiment and you collect the data in a way that you can prove or disprove your null hypothesis. So in statistical analysis, you are trying to relate quantity with quality. You're trying to relate the data with what you are trying to observe. Because hypothesis is mainly qualitative, right? Hypothesis is quantitative. Qualitative data is quantitative. So you want to relate the quantity with the quality, right? Data to reject the null hypothesis. Data to reject null hypothesis to prove the hypothesis through statistical analysis. Okay, there are three subtypes of experiments lah. I think this you can read more on your own later on, but I just quickly walk you through due to time constraint. There are three types of experiments because of different conditions, different participants, different ways we set up the groups. We can have pre-experimental research design. This one is to explore the idea. We can do quasi-experimental research design. Now, this is an experiment, but we make a lot of assumptions. Quasi-experimental design is easier to be set up, but it's not as accurate as true experimental design. True experimental design is pure experiment, very scientific. Quasi is we try to our best effort to do a true experimental within the constraint. All right. So the next few slides actually explain the differences. So I'll begin with true experimental research design. If you are doing studies in quantum computing, for example, you are probably doing TERD, yeah. True experimental research design. You use hardcore statistics to reject a null hypothesis. Okay. You have a control group and experiment group. A control group is that you do not introduce any of the factor. An experiment group, you introduce a factor and we want to see whether there be differences or not after that, before and after. We want to establish the cause and effect relationship. And both group, the members of the both group, you must randomly select from the sample. Yeah. One example of one very good example of through experimental research design is Solomon 4 group design. There are a few types of TERD, but Solomon 4 group design is one of the best setting to do it because it can reduces bias in the research. Okay, you use Solomon 4 group design when you suspect that the experiment itself is causing bias, because when you do experiments, sometimes the participants know that it is a controlled environment, so the result may become affected by it already, right? So how do we get rid of this bias? So we can use Solomon 4 group design. But in that case, why don't we do Solomon 4 group design for everything? The answer is, if yes, you can, but Solomon 4 group design is troublesome. You need more people, you need more time, you need more budget to do. So sometimes people will not do it because of the constraints. Example of Solomon 4 group design. How does it work? So instead of having two groups, normally we have two groups, before and after, right? Control group and experiment group. Usually we have two groups, but in Solomon 4 group design, we are having 4 instead of 2. So how is it different? Okay, see here, random assignment, we pick up 4 groups, 1 experiment group, 1 control group, 1 experiment group, 1 control group. So experiment group 1, experiment group 1, control group 1, experiment group 2, and control group 2. Now, for the first group, you do pre-test because you want to get some data. You do pre-test. And then for the experimental group, you do the treatment. You introduce the factors. The other one, you don't introduce. Control, right or not? Control, you don't introduce modification. You leave it as it is. Then after that, you do the testing to see any changes or not between the experiment group and the control group. All right. Now, this is what we usually do in normal through experimental research design. We just need 2 groups only, experimental group and control group. But in Solomon group, they introduce another 2 groups, experiment group 2, control group 2. Now, the difference is that in experimental group 2 and control group 2, we don't do pretest. We straight away apply treatment on the experimental group 2 and see and after that only we do the testing. We see if there's any difference between experimental group and control group. Yeah. Now, what is the difference between group 1 and group 2? In group 1, there's pretest. In group 2, there's no pretest. Why? Because in group 2, we don't subject them to pretest because we worry sometimes when we do the pretest, it will affect the accuracy of the result. For example, let's say you are a teacher, okay? You are a teacher, and in your classroom, you want to know after the students follow your class, do they improve or not? So what do? Do you give them a pretest or not? That means pretest is something that you give to them before you start your lesson. And after your lesson, you give them post-test, same test, to see whether they improve or not. Correct or not? So this is pretest and post-test. But wait, if I give them pretest, and then they repeat the test again after the lesson, of course they will do better because they have seen the test first time, right? Because in reality, we don't give pretest. We do the lesson, and then by end of the year, we give them the real exam. Just one test only. Right or not? So if we give pretest, of course it will affect the result because they have seen the question already, and then they sit for the test again. Definitely, they already know the question, and they might be able to answer better, isn't it? So that is what we call bias. Yeah, bias that is introduced through the experiment. So to eliminate this bias, we have 2 other groups to see whether the pretest has any impact on them or not. So we will find the differences between group 1 and group 2 where there is pretest and there's no pretest. So later on, the result can be calibrated, adjusted accordingly. Then the second experiment type is quasi. Quasi means pseudo. Now, why we use quasi? Of course, the best is to use through experiment, but we use quasi experiment when we have some constraints. That means best effort, best effort. So when this happens, we use quasi. Some research, right? Some experiment, there's no way for you to do through experiment because of limitation. For example, timing to do the treatment, and then not enough participants, you don't have enough participants, maybe you only have 10 participants, but actually if you should at least have 30, but you only have 10, then how? We still proceed with the experiment, right? But we cannot say it's true experiment because there are some bias there, because we cannot afford to, there are some constraints, we cannot fix the constraints, so we just go ahead. This is called quasi. All right. So one of the way to fix that, right, when we don't have enough sample, is to repeat the experiment multiple times. So you have time series lah. Yeah, you have multiple time series. So okay, let's say you can have experimental group and control group. Yeah, and then we do it multiple times. Okay, we introduces the treatment, and then we take the measurement over the time series. All right. So some of the fields that are that use quasi is educational field. Like when you are using students as a samples, consumers. Because this is in the field, it's very hard to control. So quasi is usually used in the field study, but through experiment inside the lab. Okay, so this the other one is pre-experimental. So just remember we have through, we have quasi and pre-experimental, right? Pre-experimental is for testing the environment. Is to explore before we decide to go deeper into the research. We want to see whether it's worthwhile to pursue this investigation or not. Yeah. So we can do survey. Survey is one example of a pre-experimental study, preliminary study. Yeah, you can do one simple case study, or you can do pre-test, post-test, or you can use the same control group. You can use control group on top of experimental group. That means you have two groups instead of one group. So these are three configurations that you can have for pre-experimental research design. So this is a summary of experimental research design, pre, through, quasi. All right. Pre-experimental design, okay, in layman term, survey. Through experiment is lab. Quasi-experiment is usually for field because there are some limitations, some constraints. All right. Now, let's compare the different techniques for each experimental design. Okay. Now, in one short case study, yeah, you get the group to be exposed to the treatment, yeah, to be exposed to the factor. Then you do the observation, one time case study, yeah. And then if you're using one group, pre-test, post-test, you observe before the test, O1, then you introduce the modification or treatment, then you observe again as post-test. Now, if you do static group design, you have experimental group, e.g., and control group. Control group, of course, you don't expose it to any treatment. You just observe it. Whereas the experimental group, you introduce the treatment or factor and see what happens after that. So you compare O1 and O2 to see if there's any difference or not. So this is called pre-experiment or preliminary studies. Now, for field study, due to time constraint, due to constraint of samples, sometimes you cannot have too many subjects for the experiment. Then you're repeating the subjects again and again. What you can compensate is by repeating the experiment on the same group of people. So what you do is you observe, like every 1 week observe. Then you introduce intervention or treatment. Then you observe it again after the treatment every week. Observation 1, 2, 3, 4 after the treatment, and see any changes or not. Or if you have slightly more people, then you can have one control group and one experimental group. Again, the same thing, just that you have control group. In control group, there's a typo error here. You don't subject it to, I mean, you just give them a placebo. That means you don't give them the actual modification. Okay, let me give one example. We're testing a new drug for COVID. We're testing a new drug for COVID. So we get 20 people. So 10 people in experimental group, 10 people in control group. So in the experimental group, we will let them, we observe them for every week 1 until week 5. Then we give them the new drug. Same goes for control group, but we don't give them the new drug. We just give them Panadol. We just give them Panadol, but they do not know it's Panadol. They think it's the new drug. And then after that, we observe again for a few weeks and see whether there's any difference between experimental group and control group. If no difference between the control group which takes Panadol and experimental group which takes the Panadol, that means the drug is not effective. But if there is difference, that means the drug is somewhat effective. Then we have a true experimental research design. As I have mentioned just now, Solomon-Fowl group design is most reliable because it can remove the bias of pre-test. Yeah. In Solomon-Fowl group, we have experimental group 1, control group 1, experimental group 2, control group 2, whereby in both EG2 and CG2, there's no pre-test. There's no pre-test to nullify the pre-test effect on the subjects. Okay, a part of Solomon-Fowl group design, we have a post-test only. That means, you see, for the experimental group and control group, we only do the testing afterwards, not before. Yeah, afterwards. Whereas for pre-test, post-test, control group design, we have an experimental group and control group, but we do the testing before as well as after. Now, how is this different from pre-experimental research design? You see, pre-experimental research design is simple. We just want to do a quick one because we want to check whether this experiment should be continued or not. That's why you see we only have one group. No need so many groups. Reduce time, reduce budget. Yeah. If you want to have a control group also, we just take pre-test only. So we just do post-test only. Whereas in a true experimental design, you see, you have pre-test, post-test, control group, experimental group. The best one is the Solomon-Fowl group design, but this one will incur more time and more budget. More complicated. I also need to have more people, more subjects for testing. So how much experiment do you need to repeat? 1, 2, 3, 4. The more the better, actually. That's the answer. But of course, we all have time constraint, right? So according to Gail P. Taylor, yeah, from San Antonio, minimum 2. Yeah, minimum 2. You repeat it 2. Preferably the second time you repeat in different setting. And then how many samples? Minimum you need to have 2 samples. One is experimental group, the other one is control group. If you have 4, it's better because you can use the Solomon-Fowl group. Yeah. Experimental group 1, experimental group 2, control group 1, control group 2 to test whether the pretest has any impact or not. And you must have at least one independent variable. Okay. Experimentation, even though it's nice, but it has disadvantages. You need to be supported by grant because you need money, right? And then also people can argue, okay, you're doing this in the lab. How do you know that it works in the real world? In IT, it's not just in the lab. You have to put it in the real world, right? And then if your methodology is not good, your whole result can be ignored because experiment requires scientific result, a scientific method. If your methodology is not scientific, raises a lot of questions on its validity, your result can be thrown away. And you may need to repeat again. And some more, not all variables can be manipulated because if you want to form a hypothesis, you need variables and you cannot play around with the variables. You cannot do experiment, right? Some variables cannot be manipulated easily. So that is an obstacle, a challenge. Now, about experimentation, right? I mentioned experimentation is just one of the research methods. There are others, maybe theoretical method. You can do correlational to see patterns between two variables, maybe mathematically. Yeah. You can do exploratory. Okay. That means you actually it doesn't have to be in the lab. It can be observing it in nature, in the field, basic observation. It can be descriptive, yeah, by doing by observing, by reading, yeah. And then you can do causal researches. In causal researches, even though in experiment we are also looking for cause and effect, right? But in experiment, we already have hypothesis. Experiment must have hypothesis to see the causal effect in hypothesis. Whereas in causal research, we don't have a hypothesis. We are just observing. Is there any causal relationship, cause and effect relationship between two variables or not? Now we can start by doing any of these four types of researches, and we can confirm it by doing experimentation. Yeah. So experiment requires hypothesis. The rest of this, no, it's more of a preliminary investigation. So after you have acquired the research result, what do you do with them? You do analysis, right? So the next few slides are actually talking about how you do analysis. So these are the statistical tools that you can use. Now you have to ask yourself, what are you analyzing? Are you looking for differences before and after? Or you are looking if there's any relationship between the variables? These are two very different goals, no? You want to look for difference or you want to look for relationship. And then you look at the type of data. Number two, the type of data. Is it a continuous data like time, height, weight? Or is it ordinal? Ordinal data is not like weight, height, no, but it is like, for example, let me see. It is qualitative, yeah. But there is an order. It's qualitative, but there's an order like number one, number two, number three. You can arrange it. That is called ordinal data. For example, okay, in test, in exam, you have a grade A, grade B, C, D, E, and F, right? F is for fail. So you arrange it A, B, C, D, E, F, right? So there's an arrangement. If there's arrangement, that is ordinal. Okay, nominal data means is qualitative, but there is no arrangement. Like, for example, male, female. Which one first? Can you say male, female? Can we put female, then male? There's no concern, right? Either way also we can, right? So it's called nominal. But ordinal different. Ordinal, you have a sequence. Continuous is quantitative. Yeah, it's quantitative. And there's a continuity. Like, for example, your height from baby until now, your height keeps growing, right? Continuous. And we use continuous, ordinal, nominal data for finding the difference. For finding relation, we use nominal, continuous, ordinal as well. Yeah. And the goal here is to find the right statistical test. Now, this statistical test, right, is from mathematics, statistics. You can actually use Excel or some tools like SPSS to analyze the data, or it can be pen and paper if you want. Yeah. So you'll be asking yourself whether you're looking for difference or relationship, whether the data is continuous, ordinal, or nominal, and then whether you have paired and unpaired data. Paired data, that means the two groups have relation. Unpaired means two groups are independent. Yeah, you have more than two. Because remember just now we have control group, we have experiment group, right? We also have experiment group before and after, you know. So that is where paired unpaired is coming from. Yeah. And then we also need to ask ourselves, is there a distribution, a normal distribution for this kind of data? Some data, we already know that there is some kind of distribution. It's following normal distribution. Then we can use uh, statistical tools based on this certain distribution. Yeah. For continuous, we have a t-test. T-test, maybe you have heard of z-test, but z-test we don't use it because z-test is not reliable. We use t-test, and if we have more than two groups, then we use ANOVA. All right. And then for ordinal, you know, we can use Wilcoxon, WMW, fragment, Kruskal-Wallis. For nominal, we can use McNamara or chi-square. Yeah. And then for relationship, we have additional tests like Pearson correlation or the better known linear regression. If there's a linear relationship, it's called linear regression. That one's different. I think everybody knows about it, linear regression. Or we can use Spearman correlation. Okay. So what is distribution? Distribution means that if you collect enough data, when we arrange the data in a histogram, we will see some pattern there. Like this is what we call normal. It looks like a bell. Yeah. The more, the better. It looks more like a bell. But sometimes the data collection may be skewed towards left or skewed towards right. Yeah. Or maybe there's some pockets, some holes here and there. Now, if you get a distribution that looks like this, it is still considered normal. As long as it looks symmetrical, it is still considered normal. But because we don't have enough data, that's why it looks like this. When you have a lot of data, it will look more normal. Yeah. Now, we can use a test with distribution if it's normal, symmetrical. If it is skewed, right, we still can use it, but we need to collect more data before we can do the testing. Now, if it's highly skewed, yeah, it's highly skewed, or a lot of empty holes here and there, then we must use non-parametric tests. So just now, you see, there are parametric tests such as repeated measures ANOVA, one-way ANOVA, paired t-test, and paired t-test. For if there's no normal distribution, then you can use fragment, Kruskal-Wallis, Wilcoxon, WMW. Yeah. Same goes for relation. If there is a normal distribution, you can use Pearson or linear. If there's no distribution, there's no clear distribution, then you use Spearman correlation. So what is unpaired versus paired study design? Now, unpaired means both groups are independent of each other. Let's say we have this sample. We have 8 people, and we break them into 2 groups. One is treatment group, the other one is control group. Control group means we don't do anything at all. Treatment group means we apply the treatment. Okay, so we randomly select these people and put them into 2 groups. One apply treatment, the other one without. Okay, so are these 2 groups related? Not related. So these are called unpaired because they are not related. They are independent of each other. Whatever happened here is not affecting here. Whatever happened here is not affecting here. Independent. Now let's look at a paired group. Now let's look at this example. Now in this sample, we have 1, 2, 3. We have 8 people, and they have their weight here: 80 kilograms, 70 kilogram. The blue color one is male. The red color one is female. So we are pairing them up. Okay. The first pair, okay, randomly assigned. The first pair happened to have 2 guys. The second pair happened to have 2 girls. The third pair, both guys. The fourth pair, all girls. It can be also guy girl. There's possibility because it is a random pairing, right? So one of them only is given the drug. The other person is not given a drug. So for each pair, one is given drug, the other is not given drug. So there is a pairing here, right? There's a pairing here. So when this pairing is done like this, we can reduce bias such as gender, age, because you see, some of the pair is both guys, some of the pair is both girls, some pair may be guy and girl, but here happen that only all guys or all girls lah. All right, and they are of different weight, different age. So we want to eliminate the biases, the demographic biases. Another PET study is in terms of time. You see, the same group of people, we subject them to treatment, and then we study them afterwards. So it's still the same people, same group of people, right? So this is also another PET study, just that taken at different time frame, pre and post. Okay, and then this is an example of a PET study. Another example of PET study. You see, there are 3 patients. We we extract blood from these 3 samples, and from each person, we extract the blood into 2 separate petri dishes or well. The first petri dish, we don't do anything. The second petri dish, we add some drug to it. And this we repeat for all the other patients. Okay. So again, this is PET, right? Because you see, from the same person, we have 2, we have 1 control group, 1 experimental group. Yeah. So after some time, we analyze the difference between the control group, control and the experimental for each person, and then we get the mean. Now, the other type of test is called nominal test. Nominal test is to find how many percentage. We want to find the proportion. Now, in this example, we want to assess whether the pesticide treatment on infected and non-infected plant has any impact or not. So we are introducing a new pesticide. So we apply the pesticide, the first brand, treatment A, the second brand of pesticide, treatment B. And for both these pesticide brands, right, different brand A and brand B, we apply them on infected plant and non-infected plant. So the non-infected plant is actually a control group lah. And then infected plant is the experimental group. Okay, I want to see how many percent of the infected, non-infected is recovering. How many percent of the infected is recovering after the treatment has been done for both treatment A and treatment B. So we can also assess correlation, such as using unpacked chi-square test. Okay, like in this case, we know that lung cancer and smoker, they may not be related, but we want to see whether there is any relationship or not. So we do this chi-square test. So we find out lung cancer patient and ask them, do you smoke or not before this? 60% says they smoke, 40% says they don't smoke. Then we also investigate healthy patient. We ask them, and then find out 800 smoke, 7,200 do not smoke. So this data is going to be used for unpacked chi-square test. For data relationship, we can use Pearson or Spearman. Pearson if there is a distribution. Spearman when there's no distribution. So in correlation, we try to see whether there's any relationship between 2 variables. For example, in this case, the body weight, BMI, body weight, height, BMI, and blood pressure. So if there is a strong correlation, we may be able to identify the linear regression for prediction. So if, let's say, we have look at the second example. Yeah, look at the second example. It is blood pressure versus age as compared to blood pressure versus BMI. Yeah. So in this case, you see, for people from the age of 20 to 30, they can have blood pressure as low as 114 to 116, right? And then for somebody of age range 60 to 70, there'll be a few readings. All right. So in this case, we need to use a Spearman correlation. Yeah. What if I only have one sample? If you have one sample, you can use the following test: one sample t-test, Wilcoxon, chi-square goodness of fitness, yeah, or one proportion z-test. Now, z-test is easy to use, but it is not so accurate lah. It's better to use chi-square because z-test is assuming that the distribution is normal. Usually, the distribution that is normal is hard to be used because many of the samples won't fall within the normal distribution. So it's better to use t-test or chi-square. An example of one sample test. Yeah, examples of one sample test. Now we have a blood pressure taken for 8 individuals. These are the readings, and then the mean. Yeah, the mean is 123.5. All right. So we want to know whether the mean here is actually similar or different from the population mean. So this hypothesis 0 is the population mean. That means generally we believe this is a normal blood pressure for most people. But when we do the experiment, we find out it's 123.5. So is this 123.5 significant or not as compared to 120? So we can use a one sample test for that. Now another example is we want to compare sample proportion. Okay, P, yeah, P bar 39% versus hypothesized proportion of 50%. P0. This is a hypothesis. So is this 39% considered statistically similar to 50% or not? So we can use z-test. Even though, okay, this is 39, this is 50, right? But is this difference big enough or not to argue that the hypothesized proportion is wrong? So we can use z-test to test it, or better use chi-square. Or we can, if you want to compare observed frequencies against expected frequency, maybe expected frequency is what we believe. Most people believe that we should get 33.33%. But when we do the experiment, we get 30, 40, 30. So what? So if the frequency is different, so what can we say about it? So we need to compare with the expected frequency, what we used to believe, right? Is this result significant enough to overthrow the expected frequency? How do we know it's significant enough? We use a chi-square goodness of fit test, to analyze if the percentage is below certain alpha, then we can do the rejection. So how to choose the statistical test? The summary. First, you need to know whether one sample or many samples. Yeah, one sample you use the one on the left, many sample you use the one on the right. And then you need to figure out whether your purpose is to find out difference or correlate or relationship. Yeah, difference or relationship. And then you have to determine whether the data is continuous, ordinal, or nominal, and then whether the data is paired or unpaired. Okay, is there any normal distribution or not? And then how many groups? These are the 6 things that you need to think about when choosing the right statistical test on your data. Okay, let's look at one example uh, of using unpaired t-test. Yeah, when we have more than one group. Yeah, so we have one healthy group. Okay, and one group of people with one group of people, sick people. So healthy people versus sick people. So we take the blood from them, from each group. Okay. Now, ask yourself, what is the purpose of this? We want to see whether there's any difference or not. Here we want to study inside the blood how much white cell, because we know white cell is present when we have sickness, right? When we are not sick, we don't have white blood cell in our blood. We have less. So we want to see whether this is true or not. So we are repeating the experiment. People who are sick and people who are not sick. So we expect that people who are sick will have a more white blood cell concentration. People who are healthy will have very, very much less white blood cell concentration. So the question is there any difference or not in terms of the white blood cell concentration? And then the data that we collect is the percentage of white blood cell, right? It can be 1%, 1.1%, 1.2%, 5%, 5.1, 5.2, 5.3. So it's continuous. The data is continuous. Is the concentration of white blood cell following normal distribution or not? We do not know. In this example, we do not know. So we just leave a question mark there. Then the experimental design, you see, is unpaired because healthy people and sick people, these two are very different people. If they are paired, means that healthy people that become sick later on. So these are paired. But no, they are two totally separate people. One healthy, one unhealthy. So they are unpaired. Number of groups, 2. So using this information, we look for compared differences, look for continuous, okay? And then we have a assumption for parametric test, right? So we do not know. So we use both yes and no. Use both yes and no. And then we will choose unpaired, not paired, unpaired. And then because we have 2 groups only, right? So we use unpaired t-test. Okay? So by right, they should, because we do not know whether there's any parametric, whether there's normal distribution or not, right? So we will use unpaired t-test for yes as well as no. Yeah. When it is no, then it should be oh, but it's already ordinal, right? It's already ordinal, so we cannot lah, because this one is continuous. So definitely we are just using unpaired t-test. We cannot use fragment Kruskal-Wallis because that one falls under ordinal, and then we know the white blood cell concentration is continuous, not ordinal. Case number 2. We have a new fertilizer. We want to know whether this fertilizer works or not. We want to know whether the new fertilizer works or not. So a pair of plants are chosen. So the first pair, plant A, plant B. Then the second pair, third pair, fourth pair. Then we randomly choose one of them. We then randomly choose one of them. And then one of them we put fertilizer, the other one we don't put. So after some time, we see whether they are growing or not. So here again, it's not to see relationship, right? It's to see difference between first group and the second group, right? And then the scale of the data is ordinal because it's not continuous. Because the answer is grow or don't grow, so it's ordinal. Yeah. And then one is bigger, one is smaller, right? So there is a sequence. So it's ordinal, not nominal. And then here we have data that is not following any distribution, so we put no. And then the experimental design is paired because we are using the same pair. We are using the same pair for comparison. And then the number of groups is 2. One with fertilizer, one without fertilizer. So how do we choose? We look at difference, ordinal, non-parametric, okay? And then we choose pair. And if more than 2, then we use the bigger group one, like this one. Difference, the ordinal, go to pair, okay? and then choose the paired one. Case number 3. Okay, case number 3. We have a fish from 3 lakes, Lake A, Lake B, and Lake C. Okay, we want to see the size of the fish in the 3 different lakes. So we measure their weights. Okay, and then we want, so here we are finding the differences of weight. And weight is continuous, right? And then is the test having any distribution? If we know, we put yes. If we do not know, we just put question mark. That means we have to try both. And then the experimental design is unpaired because you see the fish, there's no pairing of the fish. And number of groups is 3 groups. Yeah, 3 groups. So you see here, difference, continuous, assumption. Because assumption, yes and no, right? So when yes, we use ANOVA. When no, we use Kruskal-Wallis. Because there are more than 2 groups. Another case just now, like the relationship between lung cancer and smoking. So this one is not to find difference, but to check relationship. And then the data is nominal. Nominal. Either you have cancer or you don't have cancer, right? Nominal. It's not ordinal because there's no sequence to it. And it's also not continuous. And then it's unpaired because we don't pair the subjects at all. So we choose nominal, unpaired, chi-square. In case 5, okay, we have body weight, BMI, and blood pressure, and we do the plotting of the data. And here you see, you want to find a relationship, whether there's a relationship or not between BMI and blood pressure. The scale is continuous, and then assumption for parametric test. Let's say we do not know whether it's normal or not. So in this case, relationship continuous, and then we use both Pearson as well as Spearman, because we have no idea whether they have a normal distribution. And then how do we reject the null hypothesis using any of the distribution? Whether if you have distribution, how do you reject the null hypothesis? Whether using chi-square or t, yeah. Okay, so a normal distribution, we have the following 6 standard deviations lah. Then the first standard deviation is plus minus 68%. 68% of the population will fall under negative standard deviation from the mean. Okay, the center is the mean. And then 95% will fall under 2 standard means before and after the means. Yeah, and then finally, the third standard deviation is almost majority, 97%, 99.7%, almost everybody in the sample will fall within plus minus 3 standard deviation from the mean. So first, you need to figure out the null hypothesis. Okay, first you determine the hypothesis, determine the null hypothesis, and then we need to do the tail test. So what's tail test? Look at the normal distribution. We have 2 tails, left-hand side tail and right-hand side tail, right? So let us say we want to see 99.7% of confidence. So we will determine the significance level. Yeah, we determine the significance level by minusing the alpha is a significance level by minusing the p-value. Yeah, by minusing the p-value. In this case, the p-value is 99.7, 95, 68. The number is fixed already if it's normal. So we need to determine the significance level by subtracting. For example, if we have a confidence of 99.7%, then the significance level is 0.01. If we want to have a confidence level 95%, then the significance level is 0.05. Okay, so we have to do some we have to determine the significance level alpha first. Okay, then based on the data we have collected, right, we determine the mean. All right, and then we use a z-test formula, okay, to calculate the p-value. You can use z-test or t-test, okay, to determine the p-value, the probability value. All right, part of z-test, t-test, you can use chi-square, ANOVA, depending on the 6 questions that you need to ask yourself just now. You have to choose the right statistical tool. Then the p-value is used against the significance level to accept, to reject or not to reject the null hypothesis. So what you must remember, first you figure out the hypothesis. Example here, let's say we have a question, a problem here. Suppose that cash flow for quarter 4, okay, and cash flow for quarter 3, CF quarter 4, CF quarter 3. We want to know, this is finance, we want to know in quarter 4 whether we make money or not. So if we make money in quarter 4, that means CF Q4 minus CF Q3 must be more than 0. That means there's a difference between quarter 4 and quarter 3. We're making more money, right? So that means the cash flow is improving. The business is making more and more money every quarter, right? So this is the hypothesis. We are making money. The business is making money. So the null hypothesis is what? The null hypothesis is that not making money. Not making money means that quarter 4 minus quarter 3 is 0. Quarter 4 minus quarter 3 is 0. So that's the null hypothesis. So once we have the null hypothesis, forget about the actual hypothesis. Just look at the null hypothesis. Then what happens is that we use the data to come up with the distribution. Okay, to come up with the distribution. We assume that it's using normal distribution. Then we can use, if you use normal distribution, then we can use the magic numbers in normal distribution to determine the significance level, 0.05, 0.01. Then we apply the statistical tool to determine the p-value or probability value of the population. Now, the p-value here, you can use any one of this, one sample, t-test, Wilcoxon, blah, 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 blah. Depending on the type of problem, you choose the right test. It gives you p-value. All this will give you p-value. Once you get the p-value, okay, once you get the p-value, you compare the p-value against the significance level. So if you want to have 99.7% of confidence, right? We want to have 99.7% of confidence. We look at the p-value, see whether compare against 0.01. If you want to have 95% of confidence, we compare the p-value against 0.05. Now, if the p-value is less, we can reject. Yeah, if the p-value is less, we can reject. Yeah, if the p-value is less than the alpha, let's say our p-value is let's say 0.005. 0.005 is less than alpha, right? 0.005 is less than alpha, 0.01. So we can reject the null hypothesis. If we reject the null hypothesis, that means the hypothesis is correct. If we reject the null hypothesis, the hypothesis is correct. If we fail to reject the null hypothesis, then the hypothesis is not correct. So that's how we use experimentation. We use the instruments to collect the data, and one of the method to do research is experimentation. So from the experimentation, we make use of data to come out with the result, right? The result, we can use statistical tool to come up with the right result using any of the statistical methods, and then we can use the result, the p-value, to reject the null hypothesis or to be unable to reject. Our goal is to reject the null hypothesis to prove that our work is correct. So that's all about it. I have shared with you the instrumentation and experimentation, as well as a very high-level overview of how we use a statistical approach to reject null hypothesis. Thank you very much. If you have any question, I'm opening it now.